Lesson 75, force distance graphs. We'll be able to describe and use force distance graphs. They can be called force displacement graphs as well. It doesn't matter too much, but it's just a different name. Now, this is not really a groundbreaking, earth-shattering brand new concept. I didn't really necessarily want to give you, I want to teach you guys about energy this week, but I thought to myself, one, I have to teach this stuff first, and two, I'm going to save energy for our double lesson, which would be tomorrow. And the advantage of that means is that I'm going to spend a lot of time tomorrow working through stuff. I'm going to go through kinetic energy, potential energy. I may even discuss elastic potential, but I haven't gotten there yet. I haven't figured out what I'm going to do. But I thought, let's just clear out a nice, quick and easy lesson today, just so that we can put that in our books. So, what did we do last time? Last time we talked about work, which is why the question today was about work. Work is essentially force times displacement. It's measured in Newton meters or joules. It's essentially when you push against something. It's when you push against the force. So, for example, with the popcorn bag on the right, the popcorn bag is pushing against the force that's holding the bag closed. If you again pull against the magnet, then that would be doing work. If you're going to lift something up, you're doing work against gravity. So these are all ways in which work can be done. You need to be doing a force. So you can't just do, even if you're like, oh, you put on the accelerator so you could speed up your car, that's going to be doing a force over a distance. And sometimes there's also a force over displacement. So if you go around in a circle, then you would essentially be doing no work because your displacement would be zero. There was a question in the textbook that I've decided not to give you guys to do, and it was, in my opinion, a bit too confusing because it was a bit like, oh, we're going to talk about dealing with spinning something in a circle. I'm like, oh, I don't want to. We're just going to ignore that. So next up is we did an example. And this is pretty much the same type of example that we did just then. We worked out the force of gravity acting on the weights, which is 50 times 9.8, which is about 500 newtons. And we multiplied that by 1.9 meters, which is about 2. So our answer was a little bit less than 1,000 Newton meters. What was it? Anyway, so we'll keep going. A car is forced, and we did an example of the car. But the only difference between this example and the previous one is that we had to calculate the force. It wasn't really too difficult to work out. And then what we did is actually we decided to what I would later refer to as almost freestyle on this question. We sort of thought, well, if we now know how much work is done, we could actually calculate how much there is a temperature increase on each tire. And then we found out there was about 5 degrees, which I thought was actually just an interesting little extra tidbit that you can sort of think about. You can think about, well, okay, where is that energy going? That's going to be a common theme, especially tomorrow, but also today, is just say, well, where is that energy going? Yes, you are doing work, but that work needs to go somewhere. If you're lifting that bag of rice from the bottom of the pantry to the top of the pantry, where is that work going? Where is that energy going? If you are moving something, if you're speeding a car up, where is that work going? If you got a magnet pulling on something, where is that work going? We're going to talk about where that energy goes later on. We then did one more thing about the implications of this. I fixed this slide up a fair bit since the last lesson, but just for the record, we figured out that the amount of work, the amount of force that it's going to be pulling down on me if I'm 100 kilos is 980 newtons. So if I need to go up 1.5 meters, I said if I need to go up 1.5 meters, that's going to become 1,470 joules. Now I can expend that joules in two ways. I could go up the 2-meter stairs, or I could go up the 6-meter ramp. I've changed the answer. It used to be 5 meters, I changed it to 6 meters. And essentially what we could do is we could take that work, that 1470, we could figure out, well, how much force will I need if I go up the 2 meters? Well, if I divide it by 2, that's going to be about 750. But if I divide it by 6, that's going to be a lot smaller. That's going to be close to like 200 newtons. And it's like, well, the reason is it's easier. You require less force to go up the ramp. But it does require, you do have to pay for that. You pay for that in the terms of it's actually less, it's actually a longer distance. And that's how we talked about this. It's like, yeah, sure. If you want to lift this object, you require a lot of force. You don't require as much force to lift that object if you are, if you use the second seesaw, but you have to move it over a greater distance. And so that was what, that's essentially how levers essentially work. And that's also how motors work and stuff like that. If you think about an engine, you might think that, well, that's why some cogs are really, really big, whereas other cogs are really, really small. What the difference between those two things are is, of course, one of them moves a greater distance, and one of them moves a shorter distance. And so therefore the greater distance might, will be able to provide a greater force and stuff like that. And that gets into a mechanical advantage. We're not going to talk about that. Today what we're going to talk about, force distance graphs. Now, just for the record, a force distance graph is, this measures the amount of force applied over a certain distance. So you're measuring if pushing, and for the questions that we've had so far, those force distance graphs would be constant. So for example, lifting the bag of rice up into the air, that'll be a constant force, okay, for a certain amount of distance. But here's the problem, right? This is not always a straight, nice and easy flat line. For example, this is great for measuring elastic and springs, where the force is dependent on how much it's squished. So grab a look at this. So this could be an example of a spring. So if you squish a spring up, it can apply 50 newtons worth of force. But as it becomes unsquished, right, because as your object goes from being really, really close to further and further away, it's not going to be able to push with as much, it's not going to be able to push with as much gusto, with as much force. So therefore, as your distance gets larger, your force is going to get smaller. And this is true for pretty much all elastic things. You might actually have the opposite effect occur if you were stretching something out. Like this is for spring, but for maybe something elastic, you might pull something, and the more and more you pull it, the greater the distance, the more force that you're going to feel. So if you think about an elastic band, the greater you stretch it, the more it sort of starts to pull, the more force you can get from it. So it makes sense that not everything in this world is linear. These straight line graphs, as I said, if we go back to the other answer that we had before, this would be 19.6 newtons, because that was lifting the bag of rice. We said that was 1.6 meters, and so then therefore that's how we got 31.2 or whatever it was. I can't remember. I already forgotten. 31.2 joules, just because that was what that was. That was the length times the width, and that's what we sort of work out here. At the very bottom, I sort of say the area under the graph is force F times S, because it's your force times your distance displacement, or the work done. So if you squish a spring 15 centimeters and it can provide 50 newtons when it's 50, we can actually work out what that is. All right, so how do we do that? How do we work this out? Well, what we need to do to work this out is we can just, what we do is we just go like this. How do we work out first time? Well, we've got a triangle here. Let's power through this. Well, triangle, area of a triangle is half the base times the height. The base in this case is equal to 15 centimeters, but let's change that to meters because remember it's Newton meters. So let's call that a half times 0.15 times 50 centimeters, 50 newtons high. A half times 0.5, so 1.5 times 50 is going to become 0.5 times 0.15 times 50 gives us 3.75 Newton meters or 3.75 joules. So that's how much energy we can get out of compressing this spring, or maybe by, yeah, whatever. And of course, this doesn't have to be a spring. It could be, as I said, it could also just be someone pushing something. Maybe they get tired the longer that they have to squish it or something like that. The longer they have to pull it. I don't know. But these are some examples of how we can do it. Well, I'm going to keep this up for about another 30 seconds and then I'm going to change the slide. And I've only got 2 slides today, so okay. So next slide is just to look at some actual practical examples here. I've got 2 here, and I just want to show you. I guess I don't really expect you guys to copy these down because I'm just going to do them really quickly just so you can see how they might get done. If you guys want to copy them down though, I'm not going to stop you, but yeah, these are 2 examples with force distance diagrams. The one on the left, and we've already done this skill before, that's why I'm not going to get you guys to copy this down, but it is the same skill as working out the area under a force, under a velocity time graph. So if you go back to that lesson and how we figured that out, you could do the same thing here. A filing cabinet is being pushed across the floor of an office during some spring cleaning. The force applied in the direction of its motion and its displacement are recorded. So how it's been moved a total of 3 meters. And at the start, there wasn't much force being applied, but then there was more force. Then as we got closer towards where we wanted it to go, we applied less and less force. That sort of makes sense if you think about it. If you're moving something and you want to apply less and less force when you get closer to where you want it to be, because you want friction to start to take over. How do we find out the area of this? We want to find out the work. The work equals the area. So to find the area, we're going to find the area of a trapezium. If you don't know the area of a trapezium yet, look it up, but it is half A plus B all times H. A plus B being the top and the bottom. Luckily for us, these are all measured in meters, so I don't need to deal with converting them to centimeters. So half, the top is between 1 and 2, so it's 1. The bottom is between 0 and 3, so it's 3 times the height, which is 150. That's going to become 300 Newton meters. Yeah, so that's pretty. I'm pretty confident with that area because half is going to be 2 times 150 is 300. That's how I worked that one out there. Now, if it was a different shape, if it had like a rectangle or a triangle on top of a rectangle, you may have to use a different calculations. But yeah, it's just finding the area. And if you really wanted to, you hate remembering trapeziums, yes, you could cut this into 2 triangles and a rectangle. That would still work. It would just take a little bit more time. On the right, though, we've got another example here. We've got, and this is more reminiscent of the other ones where we were like, okay, so sometimes you're just going to have to, you know, make estimates. Give your answers. So it says estimate. In this case, we've got a jogging shoe. While jogging, a person's shoes stretch by an average of 3 millimeters with each step. Use the force diagram. So this makes sense, of course. So the more that you stretch your shoe, the more it's going to want to spring back, so the greater the force. Of course, you can see with this shoe, it's not a linear line. There comes a point where it's like, it doesn't matter how much you stretch it, it's going to pull back with the same amount. Now, how would I calculate this? There are two sort of ways that you could approach this. You could approach this by sort of creating a trapezium and then working that out. Or you could do the lazy approaches, which is what I'm going to do, which is this. I'm going to work out. So one box. What is the area of one box? The area of one box is 0.001, because that's how much is times 10. So therefore, each box is worth 0.01 joules. So then I go, how many boxes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Then we'll look for half boxes. So that one there is probably 28, 29, 30, 31, maybe 32, and then 32 and 32 point, I'm going to call that 75 boxes. So if I go 32.75 times 0.01, that means we've got 0.3275 joules. And that's my guess. That's my estimate. Obviously, you guys might get a different estimate. You guys might get a higher number, a lower number. If you probably do the trapezium one, you'll probably get a lower number. But, you know, it doesn't matter. It just has to be an estimate, the amount of joules put in here. And I think I got my signs correct, but if I haven't, please feel free to correct me. Ladies and gents, so that's how you find the work using force, a force distance graph.